For decades, farming relied on a simple equation: free energy from the sun, nutrients from the soil, and water from the rain. But as the global population surpassed 8 billion and climate change began reshaping our seasons, that old formula started to break. Crop failures are more frequent, transport chains stretch across continents, and the cost of fresh food rises. In response, innovators began asking a new question. If nature is becoming unpredictable, can we rebuild farming inside controlled environments, powered not by sunlight, but by electricity and data? Vertical farming grew out of that question, promising perfect crops year-round, grown right next to the people who eat them. But underneath the glowing LEDs lies a critical debate that will decide if this is a climate solution or a beautiful illusion. Are we saving fuel on trucks only to burn enormous amounts of electricity on lights, pumps, and climate control? Is this progress, or just a trade that moves emissions from the farm to the power grid? To understand this, we first look at the heart of the system. In a vertical farm, sunlight is replaced by specific red and blue LED wavelengths, running for 16 to 18 hours a day. Plants grow rapidly because every photon is optimized. But that optimization has a price. LEDs are efficient, but they still need electricity. In a country powered by hydropower or solar, this seems harmless. But where coal dominates the grid, every lettuce leaf is indirectly connected to a smokestack. Traditional farming doesn't pay that cost. The sun is free. Daylight doesn't need a cable. But traditional farming pays another cost: transport. Food grown hundreds of kilometers away moves through long, fragile supply chains. A truck burns fuel. Cold storage consumes more energy, and waste is the hidden part of the story. When Halib Beshkardes from Plant Factory explains why restaurants love vertically farmed produce, he doesn't talk about taste first. He talks about certainty. In a short transport chain, nothing spoils on the road. Nothing gets bruised. The chef uses 100% of what arrives. No cleaning, no trimming, no sorting rot from freshness. This point is crucial. Growing food always requires energy. If you grow lettuce in a field using the free sun, but throw away 40% of it before it reaches a plate, the energy used to grow that wasted portion becomes invisible carbon. Vertical farms grow with high energy, but they deliver nearly zero waste. This is the first contradiction: low energy growing with high waste distribution versus high energy growing with no waste at all. Which is better for the planet? The answer depends on geography and the local electricity mix. Now we add the second complication: HVAC. Most people think LEDs are the biggest energy consumer in vertical farms. They are not. The true energy giant is climate control. Plants transpire, releasing water vapor. In a field, the wind carries it away. But in a sealed indoor system, humidity rises rapidly. If humidity becomes too high, mold and fungus can destroy the crop. So dehumidification systems must run constantly, removing water from the air. These HVAC systems for cooling, heating, and airflow often consume more electricity than the LEDs themselves, creating a 24-hour electrical demand that never stops. This is where the grid becomes destined. A vertical farm in Norway, powered by cheap hydropower, has almost no carbon footprint. A vertical farm in the Middle East, powered by solar, can operate sustainably even in extreme heat. But a vertical farm in a region dependent on coal will produce more emissions than traditional farming, even after counting transport and waste reduction. In these regions, the grid is the bottleneck. Farming becomes as clean or as dirty as the local electricity supply. So when people say vertical farming is the future, the truth is more precise. Vertical farming is the future where renewable energy is abundant. It is not a universal solution. It is a grid-dependent solution. The debate becomes more complex when we consider land use. Traditional agriculture requires millions of hectares, often leading to deforestation, pesticide use, and soil erosion. A vertical farm requires only a warehouse. A few hundred square meters can replace dozens of hectares of fields. This brings environmental relief. No pesticides, no soil degradation, and dramatically less water use, since hydroponic systems recycle nearly all of it. Reducing land pressure is one of the strongest arguments for vertical farming. Food production stops competing with biodiversity. Forests and wetlands can remain intact. But again, the electricity that powers these farms decides whether this benefit outweighs the energy cost. Transport is often misunderstood in this debate. Many assume food miles represent the bulk of agricultural emissions. But globally, transport accounts for only 5 to 10% of a food's carbon footprint. Production itself, fertilizers, irrigation pumps, tractors, creates most of the emissions. This means reducing transport helps, but not enough to offset a dirty grid on its own. However, if a vertical farm eliminates both transport emissions and food waste, the balance begins to shift. Vertical farming's greatest strength is consistency. Every harvest is nearly identical. Every plant receives the same nutrients, light, and airflow. Weather no longer matters. Droughts, storms, and floods no longer disrupt production. With climate change creating more unpredictable seasons, this consistency is invaluable. Nations seeking food security invest in vertical farms because they remove nature from the risk equation. But energy remains the new variable. Imagine two scenarios. First, a farm grows lettuce in California and ships it to New York. A cold truck travels over 4,000 kilometers. Fuel is burned, cooling systems run, and spoilage happens. By the time it reaches the supermarket, part of it is discarded. In the second scenario, a vertical farm grows the same lettuce inside New York City. It's harvested in the morning and eaten in the afternoon. No spoilage, no freight, no warehouses. Which system is better? The answer depends entirely on the electricity powering the LEDs and HVAC. If that farm uses renewable energy, it becomes the clear winner. If it uses fossil fuels, the environmental advantage collapses. Now imagine a future grid powered mostly by wind, solar, and advanced storage. In that world, vertical farming becomes the most environmentally efficient way to grow leafy greens, herbs, and other high-water plants. The energy cost becomes clean, the logistics become minimal, and the precision of the system eliminates waste almost entirely. But until grids are decarbonized, vertical farming is both a promise and a warning. It shows what agriculture can become, but also what it cannot sustain without clean energy. There is another dimension to this debate: human labor. Traditional farming faces shortages as fewer young people want to work in fields. Vertical farms automate much of the work. Robotics handle seeding, harvesting, and packaging, while AI systems monitor plant health. These systems don't rely on seasonal labor. This stability benefits cities by making local food production more reliable. But automation carries its own energy cost, as servers, sensors, and robots add another layer of electricity demand. As technology improves, LEDs become more efficient, pumps get smarter, and HVAC systems recover more heat. AI learns to optimize conditions so plants grow with less energy per kilogram. Some farms even experiment with hybrid systems, combining natural sunlight with LED supplementation to reduce energy usage, though this requires specific architectural designs. The industry is evolving quickly, but the energy debate remains central. What most people overlook is the difference between calories and freshness. Vertical farming will never efficiently grow calorie crops like wheat, corn, or soy, which require vast open spaces. But it excels at freshness crops, leafy greens, herbs, and strawberries, plants with high spoilage rates. These crops justify the energy investment because traditional supply chains waste so much of them. So the future is not all or nothing. Vertical farms will complement traditional agriculture, not replace it. The strongest conclusion from this debate is that vertical farming is not primarily a farming technology. It is an energy technology. Its success depends on decarbonizing power grids, improving storage, reducing HVAC loads, and optimizing LEDs. Once electricity becomes clean and abundant, vertical farming becomes logically unbeatable. Until then, it remains a system that works brilliantly in some regions and poorly in others. The question we end with is simple. Should we light farms with LEDs instead of sunlight? Should we grow food in buildings instead of fields? Should we trade natural energy for electrical precision? The real answer is that this transition will happen gradually. As renewable electricity expands, as cities demand more local food, and as supply chains become more fragile, vertical farming will grow where energy allows it. In places with clean grids, it will flourish. In places with dirty grids, it will struggle. But the direction of time is clear. The world is electrifying. The grid is getting cleaner, and agriculture will follow the grid. Vertical farming is not about replacing nature. It is about engineering stability in an unstable climate, guaranteeing food where weather can no longer be trusted, and building resilience for a crowded world. The debate between energy and logistics is not a fight. It is a balancing act. And as renewable energy becomes the foundation of modern civilization, that balance will tip decisively in one direction, toward farming that is controlled, efficient, predictable, local, and nearly waste-free. The transition is not fully here yet, but the architecture is forming, and the farms of the future will grow not under the sun, but under the glow of clean electricity.